Sorry about that. Hate when that happens. So glad to be back. Let's go ahead and talk again about this problem. So you remember we started off with the 2 points. We talked about how to apply them, recognizing that A is going to be 102,000. And then we had to find B. So we did some hard work. We definitely brought our calculator into the game and we found B. So to finally answer the question, we want to actually put the entire equation together in y equals a times b to the x power. So a being 102,000 will be multiplied times b, which is 0.9836 there, and I'm going to raise that to the x power. So the next part of our mission with this problem is to use that information to compute what would happen with the number of Minnesota farms if this rate of decrease continued, and we're estimating that value for 2010. You remember we started off recognizing that we are counting the years from 1983 to the year that we are concerned about, in this case 2010, and that would be 27 years, 27. So we're going to plug 27 into our calculator within this equation, and of course Desmos is a fine way to do that. So let's get that started. So I'll type this into Desmos with x being replaced by the 27 years, and when I do that I get approximately 64,000 would be the population or the number of farms in Minnesota. And so what I want you to see is that even though we plugged in a number or an exponent that's pretty high, like 27, the fact that this is smaller than 1 makes this number drop, right? And so we did talk about exponential growth versus exponential decay. So I just wanted you to really see that, right? Because you think you put a 27 in there, it's going to be super big, but it's getting smaller and smaller over time, given the fact that we have that b value that is less than 1. All right, let's go back to our screen and check out some other examples. So here we've got simplification of expressions with irrational exponents. And what I want you to know here is that all of your old exponential laws are in place. The laws that we're specifically going to consider is this one: a to the m times a to the n is equal to a to the m plus n, and a to the m raised to the nth power is equal to a to the product of mn, or a to the m times n. And so we have both of these situations here where the two bases are the same, so we know that we are going to add the exponents. And so we get 2 to the power of root 5 plus root 3. If you were looking at this and saying root 8, you know, you made me want to cry. No, I'm just kidding. But that's a common thing. You're like, oh, we have to add them, but we cannot. We still remember that irrational numbers, we can't really add them if they're not of the same type, and therefore we're just going to leave it like this. So this is our final answer. Over here, however, we can multiply irrational numbers as long as they're being raised to the same power. And so this is a power to power move, or a to the m times a to the m to the n power. So this is going to end up being 7 to the 2 times the square root of 2 times 3, or 7 to the root 6 power. I really like exponential equations like this, where you're trying to solve for x, and you can do this with a calculator in some way, but when we begin working with exponential functions, we like to do it without a calculator so we can check out the relationship. So one thing that you want to do when you have an exponential relationship is make sure that the bases are the same, because there's this law that says if I have 3 to the a and I tell you that it's equal to 3 to the c, this can only be true if a and c are equivalent, okay? You can only have this equality of two bases if their exponents are equal. So if I say that this is true, then a and c must be equal. So that's so powerful that it makes me want to make sure that I'm dealing with the same base on either side of my equation. And so I know that 3 to the 2n plus 1 power, it has a base of 3. I know I can write this 81 as a base of 3. So 3 to what power is 81? 3 to the 4th power. So now I'm going to use this little bit of knowledge over here to set 2n plus 1 equal to 4. And with a little bit of algebraic manipulation, we get that n is equal to 3 halves. We'll do the same thing over here. Um, Here you're looking at it and you're like, well, yeah, 4 is the base. It's not, right? Because 4 to no power gives me 8. Well, we could make a fractional power, but that'll be a little bit more challenging, perhaps. I don't know. Maybe you could try it. Let me know what you do. But the easiest way to handle this is to put everything to the base of 2. So if I rewrite 4 as a base of 2, it's 2 to the second power. So that would be 2 to the second power to the 2x power. You see that because it's 4 to the 2x? And I can write 8 as 2 to the third power, again, raising it to the exponent here, x minus 1. And so what I now know is that, let me make everything just to the base of 2. So this is 2 to the 4x power, because I multiply those exponents. And this one, I'm going to do the distributive property because I am multiplying to 3 times the x minus 1. This is 2 to the 3x minus 3 power. Now we're going to enact that little law we just talked about. And we now know that this implies that 4x is equal to 3x minus 3. A little bit of algebraic manipulation gets us that x, that's an x, is equal to negative 3. Move the 3x over to the other side, and we're left with negative 3 is equal to x, all right? So before getting started with this problem, another key concept that we need to know is as long as we have a number, let's say 3 to the x power and 3 to the y power, and instead of them being equal, we see that with the same base, same non-zero, non-1 base, in fact, we want to make sure that the base is, in this case, positive, right? So we're looking at b's that are greater than 1. As long as we have b greater than 1 as we do here, if this is the case, then this is also the case. Meaning 3 to this power being greater than 3 to this power implies that x has to be greater than y. And so with that, we're going to apply that to this last example in section 10.1. All right, so again, we like to make things the same base. 256, I don't know if that rings any bells for you, but 256 definitely can be written as a base of 2, as can this 4. And so we write 2 to the second power raised to the 3p minus 1 for this particular part of the expression. And then we write this here. Well, you know what? I'm going to go a step further. I'm going to write this 2 to the negative 8th power, right? So that's reminiscent of the fact that a to the negative m power is equal to 1 over a to the m, and therefore 1 over 2 to the 8th is equal to 2 to the negative 8th. All right, so now that I have that, I'm going to simplify this over here by using the distributive property. I have 6p minus 2 as the exponent, and if we use this idea, then we know that 6p minus 2 must be greater than negative 8. And so we start our problem in the way that we do all algebraic inequalities. We're going to try to isolate the variable. And when we do that, we end up with a negative 6 here, and p is greater than a negative 1 is what we have. All right, hopefully that made sense, guys. Let me know, and if you have any questions during the week, please reach out to me. Take care. Bye-bye.